So what does the epsilon delta definition of a limit really mean? Well, intuitively, a limit means that as x approaches some number, maybe a function f of x will approach a number, let's say L. But how do we precisely define that? We know what it means intuitively, but how can we put intuition into mathematical symbols? Enter the epsilon delta definition of a limit. So what does this statement really mean? Well, it just means that for all epsilon greater than 0, there exists a delta greater than 0, such that whenever the absolute value of x minus a is greater than 0, but less than delta, then the absolute value of f of x minus L is going to be less than epsilon. So essentially, what it means is that you can give me any value of epsilon greater than 0. And if there truly is a limit, again, this is just what a limit really means, then I can always give you another number, delta, that's greater than 0. And well, why is this delta important? Well, if there truly is a limit, then whenever x is within delta of a, as I've drawn here, then f of x is going to be within a range, epsilon of L. So basically these symbols, all these symbols really mean, it's just that I can get f of x as close as I want to L, so long as x is close enough to a. And this is going to be true for any value of epsilon, no matter how big or how small. But usually in a context of limits, we only really care about small values of epsilon. So basically, if I can make epsilon as small as I want, and I can still find you a number delta, so that all the x values within that range, within a range delta around a, all correspond to f of x values that fall within epsilon of L, then I really have no choice but to say that as x approaches a, f of x sure seems to be approaching L. Or, as x gets closer to and closer to a, we're going to see that f of x keeps getting closer and closer to an L. And basically, that was the intuitive definition of a limit that we stated earlier on in the video. And we have shown that the rigorous definition is actually the exact same as the intuitive definition. So for me, this concept took a lot of time to understand because I wasn't familiar with putting symbols to intuition. So one of the first questions I actually had was how come epsilon comes first instead of delta? So basically, I thought that delta and epsilon should essentially switch places here in this first part. And I mean, my train of thought was that, well, if delta is just a range of x values and x is usually the independent variable of a function, then shouldn't delta come first? Again, the intuitive definition that we set was, as x gets closer to some value a. So I didn't really understand why we had an epsilon first. I thought we were supposed to put an x first. And, I recommend you try this alternate version of the epsilon delta definition, or the wrong definition of the epsilon delta definition. Draw the graphs and see if it captures the intuitive definition of a limit. And guess what? It doesn't. And I'll show you why right now. So I've written down the quote-unquote alternate definition of the epsilon delta, or what I thought was the alternate definition. And I'm going to show you why right now this definition is actually wrong, because it doesn't really capture the intuitive definition of a limit. So basically, in this alternate definition, epsilon just has to exist. Nothing is really going to control the size of epsilon. So let's say I say for all delta greater than 0, right? As I said here, for all delta greater than 0, right? I put where I wanted my deltas to be. And basically, again, because this is a for all symbol, that means my delta can be as small as I want. So I'm just going to put these arrows here to show that delta is going to be super small. But obviously, this figure isn't drawn to scale. Well, in this alternate definition, it says for all delta greater than 0, there exists an epsilon greater than 0, so that whenever the absolute value, or whenever x is within a range delta of a, then all of the x values have to correspond within epsilon of f of x. Well, guess what? What if I just set epsilon super, super big, right? Because again, epsilon just has to exist. There's nothing that stated epsilon had to, decrease or increase. It just has to exist. So if I make epsilon super, super big, well, then this definition would still hold true, right? As x approaches a, well, I see that all the values are within an epsilon range of L, but this epsilon is super big, and obviously that's going to happen, So this doesn't really capture it doesn't really capture the intuitive definition of a limit. So this doesn't capture the idea that, as x approaches a, then f of x is going to approach L. Because guess what? Nothing's restricting epsilon. So I'm going to erase all that, because I also had another question. And another question I was stuck on for such a long time was that, well, the intuitive definition of a limit means that as x approaches some value, a, f of x is going to approach some value L, right? Well, as I can see in the epsilon-delta definition, well, delta is just going to be a range of x values, while epsilon is just a range of y values. So, based on the intuitive definition, I should see that, as delta got smaller and smaller, then epsilon should as well. But it's not stated like that in the epsilon-delta definition, right? Because, again, I'm controlling epsilon and not delta. So, to me, it seemed like the definition was suggesting that as epsilon got smaller and smaller, then delta got smaller and smaller. And, not the other way around, which is, what I thought intuitively. In fact, both views aren't actually supported. So at a high level, we can get f of x as close as we want to L, so long as x is sufficiently close enough to a. And guess what? The epsilon delta definition never states that delta should actually get smaller. What it does state, as you can see by this implied symbol, it just says that all the values within delta of x, right? So we can see this over here. All the x values within delta of x have to accommodate for your epsilons, right? So basically, all the x values within a range of delta have to correspond to y values that are within a range epsilon of L. And it is true that for most functions, as your range of f of x values gets smaller, the range of those x values that create those f of x values will get smaller as well, right? And this just comes down to what a function is, right? Which is just a relationship between x and f of x values. So obviously, if your input range gets smaller, then your output range will obviously get smaller as well. But the exception is for constant functions. Because no matter my range of x values, well, guess what? My output stays exactly the same. It doesn't change. So the epsilon delta definition provides provisions for both of these cases without ever explicitly limiting the behavior of delta. It doesn't say that as epsilon gets smaller, then so should delta. It just says that if you so happen to choose a smaller epsilon, well, your deltas better just, accommodate for that. And it just so happens that for literally every single function besides the constant function, as epsilon gets smaller, delta will too. But it won't happen for constant functions, as we already said. And obviously this isn't going to be true for, functions that clearly violate the epsilon delta definition. So no matter how small you get around a, not all of your x values within that range are going to correspond to f of x values that are within epsilon of L, as I shown in the red. So obviously this isn't going to be true for functions like these. I mean, this just violates the epsilon-delta definition, which is why the limit doesn't exist here. I'm just talking about like normal functions, like, polynomials, exponentials, or whatever. So that is all for the epsilon-delta definition of a limit. I hope you got value from this video. And, hopefully, after watching this, you won't spend as long as I did puzzling over what this definition really meant. If you enjoy this type of no BS content, please consider supporting me by subscribing, commenting, liking, and thank you for your viewership.